What I call this event, the lecture or the demonstration of the event, okay. Called popularized science. It's a polymer experiment. So it is our great pleasure to have Professor Vincent Mareau, the University of Grenoble Alpes, and he's going to show the demonstration of the polymer experiment. He has been involved in the, the outreach activities in Grenoble, and he showed the experiment to the high school or the junior high school students, and so it's a title of this event, Popular Science. So make popular the science and polymer experiment to the students and pupils, and they try to make have an interest about the science. So that it's another important aspect of our research activities. Today he will show this kind of experiment. And I was privileged to already watch his experiments in May, and it was quite amazing. But not only he showed a very eye-catching experiment, but he also makes the student consider about the principles and mechanisms of the atoms or some basic science. And finally, let me introduce a little bit about our project of the inter-university exchange project. So this event is a kind of sponsored by this project, and we have the activities of the student exchange with the European University. The University Grenoble Alpes is one of the partner universities. So what I would like us to hear the first is have the interest of his experiment, and if it's a match to you, so that he would like to recruit you as to be involved in the outreach activity also in Tsukuba. So if you are interested in doing this kind of activity, go to the high school or junior high school around this area and show the experiment to the students. So it will be his great pleasure. And another thing, so that if you have the interest of the international exchange, and if you would like to go to Grenoble and stay for a few months or 1 year, so please let us know. So we provide some support in order to realize the staying abroad. Okay, so let's start.
Thank you very much, Sensei, for this introduction. Thank you all for coming this afternoon. First, I need to acknowledge for financial support la région Auvergne-Rhône-Alpes and the French Embassy in Japan. As it was said, I'm coming from Grenoble University. I teach in Polytech Grenoble Engineering School, and my research laboratory is CINES. So today, the idea is not to do a lecture. I did it for undergraduate and graduate students yesterday and the day before. The idea today is to show that this experiment that I use to teach can be used also to popularize science among younger students. So, Polymer in Your School project is in France at Polytech Grenoble. And we hope that it will be in Tsukuba very soon. So first I will explain what in France we do exactly with science popularization with the group Polymer in Your School. And after I will give some idea about what can be done in Tsukuba. And these are the experiments just below, the experiments that I choose for science popularization. Some of the experiments that I show before for lecture will not be used in schools because they are not easy to explain or they are not visual enough and so on. So it's a selection of the one that I presented before. So in France, the idea was developed since the last 10 years to popularize science using polymer experiments. In fact, as I teach polymer science, I do lecture and I do also laboratory with the students, and during these activities I developed special visual experiments, and the idea is to use the same experiments, but with younger people. So in France, the public starts very young. In kindergarten, they are 5 years old, the younger of the students that try this experiment or see this experiment. We go up to 18 years old or 20 years old students. The teachers that go to popularize science in France are first and second year students in Polytech Grenoble. They are 21 years old. It corresponds to L3 and M1 level. So they are, that could be undergraduate or graduate students here that could go in the schools to present these experiments. So the biggest benefit, I think, for the students of Polytech Grenoble is to learn better about polymer, because when you try to learn to popularize science, you discover sometimes that you cannot answer the question of the very young children. And their question can look strange at the beginning, but after some thought, after some more research and so on, you can find good ways to answer these questions. So it's a good opportunity to see if you masterize your science or not. It's also in France an issue, promotion of women in science. There are not enough women who go for a science career. And of course, it would be better if there are ladies that participate to the project. But that way, the young students in France can see that women do science in engineering school or in university. In France, I have every year between 25 and 30 students of Polytech who are enrolled in this project. And together, they visit something like 1,000 children every year to present science popularization activities. In France, we developed 3 different programs. There is Polymer in your school is a generic name, but the original Polymer in your school project is one of the way to present this experiment. It is about 1 hour presentation in the classroom with 2 or 3 enrolled students that present the experiment. Another way to do that is called Classroom Scientific Partner. It's organized in France by an organization which is called La Main à la Pâte, hand in the dough. I mean, do it and you will understand how it works. I should translate. This organization is nationwide, but in France, I have, let's say, 6 students that work on this project, and they go in schools for primary school, 9 to 10 years old children, and they go 5 weeks in a row. So they participate with the teacher to create an activity that will last for 5 weeks in order to make the children understand better. And the last program that we have in Grenoble is the escape game. The idea is to use the same type of material, but to make a game out of it. So the young that participate to the game, they have to think of a way to activate something, to get special numbers, to get a key, and to get out of the room. That's the idea of the escape game. So 45 minutes of game, and after that, 45 minutes of science explanation. I think to begin here in Tsukuba, maybe the classical way should be a good try to have Tsukuba students that go in classroom for a time period of about 1 hour would be wonderful. So the Tsukuba project starts today. That's the big start. It's the same idea as in Grenoble to popularize science. Here, the idea is junior high and high school students. So public should be between 12 and 18 years old. And the teacher should be the undergraduate and graduate student of Tsukuba University. Same as in France, the benefit would be wonderful to discover what you don't understand really when you try to teach it. That's still the same good way. And of course, as Tsukuba University is a really international university, it would be also a good way to mix between Japanese and international students. So they go together in the junior high and high school Also, like in France, it could be the opportunity to promote women in science. So the number of enrolled students per year in Tsukuba is something we don't know yet. We will see how it goes. Kushida Sensei, who is here, is really nice to be the volunteer to help me with this project and to be the Japanese referent for Polymers in New School. So he already knows everything about the experiment, and all of this experiment will stay here. So the material is available to start as soon as possible. So yeah, I said that the Polymer in your school could be 1 hour in the school with students. So now I will show experiment. The idea is not to teach you polymer science. I did it during the lecture. The idea this time is to show how you can proceed with the students. Of course, I will explain the experiment, and I will explain if we do this like this in France or not, depending on the age of the student and the risk and so on. So I will try to make it that way. So one experiment that we don't do in France is this one, the chain entanglement experiment. But we don't do it in France because French students are a bit maybe very agitated and difficult to control. So I think it's not possible in France. It's way too risky. But maybe in Japan, as you are very organized, maybe the students are listening better, or I don't know. So maybe you could try, okay? It's an experiment. I did it 2 times this week. It's a nice experiment. It's very visual, but it's risky in the way that if this fall apart, fall on the floor, it will take a lot of time to clean the mess, okay? So for lecture, it's okay. For science popularization, it's wonderful if you can control your environment, okay? So it depends also on the age of the students you are visiting. I will show it to you right now. So the idea is that polymer chains are entangled and they interact with each other. And if I try to fill this syringe, if I go fast enough, I will be able to fill the syringe above the level of the liquid. So I go now, and you see that I can fill the full syringe above the level of the liquid. So this is good, but if you have 20 young students, 7 years old, that wants to run to the experiment once you did it, it can become a problem. So it will be Kushida Sensei responsibility. If you want to organize this or not. Maybe it's possible to do it with a smaller amount of liquid, with a smaller syringe. That way, if there is a mess, it's a smaller mess. In France, sometimes I show also that when I push the liquid out of the syringe, the liquid is swelling. It gets bigger than the orifice of the syringe. It comes from the fact that when you have polymer chains that are entangled and you force them to go to the end of the syringe, they are stretched like spring. And once they get out, no more stretching, so it comes back, so it gets bigger. It can be something that can be shown also. I didn't show it during the lecture, but you see, regular is like this, and if I press hard, it becomes a larger diameter. It's not so easy to see, but if you want, you can explain this also. So this is the tricky experiment. Very good for lecture, maybe more difficult for popularizing science, but it can still be a try in Japan. In France, as you've seen here, this is a setup that is inside of a box. It's for a museum of science. We designed this so that students can activate it without spilling everything, without stealing the syringe, without breaking it. Okay, so it's possible, but it's heavy and you cannot go in the classroom easily with it. But that's the way we found to protect the experiment in museum. After that, we have another experiment which is very easy to carry. In France, most of the time we have smaller boxes. It's possible to have smaller boxes, but for lecture and for visualization, it's better to have a large component like this. So the idea this time is to show the impact of the chain length of polymer on the viscosity. We have 6,000 grams per mole polymer in this solution. The concentration of the solution is the same for this one. It's 30 grams of polymer for 90 milliliters of water. And for these two ones, it's only 6 grams of polymer for 90 milliliters of water. So I assume that for us, when we go to kindergarten, to explain the impact of chain length on the viscosity is not something easy. But in junior high school and high school, when we go, it's something that can be done, okay? So what we see is that if the chain length is small, there is no impact on viscosity. It looks like water. If the chain length become bigger, 35,000 grams per mole, the viscosity is like the one of a syrup. If it's 1 million grams per mole, the viscosity becomes much higher, even though there is only 6 grams of polymer instead of 30 grams in this one. So 5 times less polymer, but much higher viscosity due to chain length. So when I present this, the idea is to explain something that makes sense for children. So a good way to do it in Japan would be to speak about ramen for the long chain, okay? But for the short chain, in France, we have coquillettes, which are very small pasta. Do you have small pasta in Japan? Yes? Very small? Okay. So this one, you can explain that if you have the very small one in your soup, you can chunk your fork or your whatever you want inside of it easily, okay, your spoon. But if you have a longer one, it will be harder to shake it with a spoon, okay? So that's a food illustration that works well. And this one is a 4 million grams per mole polymer, still 6 grams of polymer for 90 milliliters of water. And the student will see that they think it is a solid. So it's also a good opportunity to show them that sometimes we think something is a solid, but it can still be a liquid if you give him enough time. So you speak a bit about rheology. And so one way to do it is to put this on the side and to say at the end of the meeting, we will see it again, and you will see that it finally gets down, okay? So this is very good for polymer illustration of chain length, because when you speak to children, it's very difficult for them to understand that polymer consists of micromolecules that looks like chains, because they never see it. We never see it either. But it's difficult for a child to understand something that he cannot see. Sorry. So in Japan, you have plenty of illustration of viscous food. So that's very, very nice for you. So you can explain to the children that what they eat that is viscous corresponds to natural polymers. And this is an opportunity we don't have that much in France, because we don't eat when it's viscous. After that, there is the idea of transition, thermal transition in polymers, the notion of glass transition temperature, to explain in France, even for young children, understanding that when you raise temperature, you will have finally something that melt, for example, or something that's softer is possible to explain because they have experienced it. So here I have a nice sponge that is a good opportunity to speak about glass transition temperature. So of course, when the children are very young, we just explain that we don't even want to tell the name TG because there is no need. We can explain that there is special temperature for each polymer, and below the polymer is hard and above the polymer is soft. So this is a sponge that is hard at room temperature when dry. And when you put some warm water, so maybe when you are in a class, you have access to water. If not, you can mix boiling water. So the students in France, they go with the kettle in the classroom, or they borrow kettles when they arrive in the classroom. And here I'm mixing very hot water with room temperature water, I would say. And that way I will have enough heat. You should go above 50, for example, or 40, to see and to show that sponge, when it's in hot water, becomes very soft. So this is quite easy to do. And in France, we have a bit of a trouble when I give this sponge. I buy a sponge every year because when my students go to the school, they show the sponge and so on, and young children, they want to take a bit of it. And so after sometimes, very short, there is no more sponge. So this can be a problem. So this sponge now is hot, so we are above the TG, so it's very soft. And if I press it and I put it in cold water, okay, so here I have iced water. It is becoming hard, and the polymer chains don't move anymore. So the good point with the sponge is that the phase changes when it's very small and hard like this, and after that you can show them that if you put it back to the hot water, in few seconds, when the temperature of the polymer is above the TG is about 20 Celsius degrees here, you have again the smiling sponge. And this is reversible. Usually children like a lot the reversible things. Something that is hard that can soften. It's something that they want to play with to see again hard, see again soft, and so on and so on. So that's like a small game. Okay. So this is very easy to do. I think you have this kind of sponge maybe in Japan, maybe not. Otherwise, I can ship some, but it's fine. Okay. Okay. We have another experiment that is quite nice and working well if my students listen to me, which is not always the case. It needs very hot water. So it happens, and my students tell me that they try experiments in front of the children and it doesn't work. So during this is something important, I think, too, in this project, is the fact that the university students will found that when you give a lecture and you show experiments, to make it work properly, it takes energy, and you need to control everything. When they arrive, my students are like this. I show them the experiment, they read a bit about it, and they try one time, and after that they say, let's go. And when they arrive, it fails. It's not working. And when they have questions, they can't answer the question. So next time they study more and we discuss and they find a way for it to work. So I think it's also a good way to learn because they discover also that failing in front of a large group of children is not something so easy, so nice. So after that, they try to put more energy to avoid failing again. So here, the experiment that can fail a lot is this one. It's TG again, like for the sponge. This time it's PET, and this PET has a TG at about 70 Celsius degrees. So I need to go quite above 70 Celsius degrees to be able to soften this polymer to go above the tissue. So usually what happens is when my students talk with the children and so on, they don't take care that much that the water is hot enough, and they pour maybe 90 or 80 Celsius degree water, and it doesn't work, and it can be complicated. So now I'm waiting for the water to be hot enough. I will pour it on top of this sample, and when I will remove it, I will be able to twist it, because polymer chains can move. We are above the TG. After that, I will take it like this to let it cool down, and we will see that it stays on its already on the shape I gave it, the twist, because we go below TG. And after that, I will put it back to hot water in order to show you that this sample has a shape memory, because when I stretch the polymer chains like spring, and then I stop moving, I ask them to stop moving because I go below TG. When I go above TG, the spring comes back and the shape comes back. So now I should have enough hot water in a few seconds. Yeah, I can use this time to show you the 4 million grams per mole solid material that finally flow and show that it's a liquid. Okay, so we have reached the maximum temperature possible for this water, and I pour it on top. So this is a bit too big compared to what I want to do. I mean, I speak about the recipient. Okay, but it's okay. So now my polymer is in the water. I have to wait, of course, let's say less than 1 minute for heat to diffuse through all the polymer. So what you can do is to move a bit inside of the hot water. Be sure that when you will remove it, it will be soft enough. So when it's hot enough, you have to go quickly and to do this twist. And after that, you have to hold it long enough so that you show that when you stop twisting it, it will stay really twisted. So now it's not enough. So if you have, of course, cold water, you can save time and do this. My students, they don't have cold water when they go in the room. Okay. So now I can show you that if I remove my finger, the sample stay totally twisted. Okay. And after that, the reversibility, so it's better in a smaller recipient so that people can see untwisting happening. But here I don't have one, but it's okay. So if it doesn't take too much time to do the explanation and so on, the hot water is still hot enough so that this will be reverted. So you can see. But I will show it in a few seconds. Okay, so now I'm coming here to show you that it is untwisting by itself. It's almost finished. So I will remove it from the hot water. And we can go back. So it stay a little bit twisted, and I can cheat and say, oh, it's perfect. But I can also explain that maybe it stay a little bit twisted because some of the polymer chains had enough energy to really move in the sample, while others were just stretched like spring, and they come back totally. The ones that really move in a translational motion, they cannot come back. So that's why there is still a bit of a twist that remains. Okay? So this was for the notion of glass transition temperature. Now I will present a part that is, I would say, very important for this polymers in your school. It corresponds to, I would say, the original first experiment, and the experiment that I do when I have very short time. Sure to do this experiment because it's the one that speaks the most to the children. I have to say now, when it's hitting again, that today I will present you something like 10 experiments. And when my students go into school, they do between 3, 4, 5 experiments maximum. But already just 3 experiments is enough to popularize science, to give the children the intention to look at science and so on. So here I show you everything that can be done in front of children, but I assume you will have to choose, because if you have 1 hour and you need to let some time to the children to experiment by themselves and so on, it will take a lot of time. So this experiment is about PCL, polycarbolactone. So the idea, this was part of my lecture. The idea, I'm not sure I will keep it. The idea is that this polymer is semi-crystalline. It is biocompatible, biodegradable, but the main interest is the fact that the melting temperature of this polymer is 60 Celsius degree. So if I put some of the polymer inside here, it's the same. And if I have boiling water, I try to adjust to be able to give all of you a small piece of polymer. So when we go to kindergarten, we don't offer polymer because the children can choke on it and it's really terrible. So when we go to higher level, it might be possible, but it still can be dangerous, and it takes a lot of polymer to offer polymer to everyone. So this is a choice you will have to do, but for sure it is always difficult to show a toy to children and not to give them. So it can be frustrating. So you will have to decide. I tried to find a Japanese producer of PCL, but unfortunately the one who was making a large enough molecular weight PCL stopped to do this a few years ago. So I couldn't find, and I contacted the Chinese producer, and I tried to have him send a few kilograms here for free, but it didn't work. So this one is an English PCL coming from France, but I'm sure you will find a way to argue and discuss.
Why it didn't work?
It didn't work with Japanese because now they make this polymer to be an additive. To be an additive in polyurethane. And they don't need long chain. This is 80 grams per mole polymer. So please shape it. You will not have that much time to play with it. Shape it the way you like. Sorry, it's not big chunk because you already have so many here. I'm kidding. Come on. Make a new doctor with me. Okay. Yes. So yeah, please shape it. You see it's hot, but it's not burning hot. It's not burning hot. It's not burning hot because even if it's 80 Celsius degrees or 85, it depends at what time you take it. If this was, for example, a tweezer, if it was tweezers made of iron, I couldn't hold it. It would be too hot. But as polymers are not conductive at all, as they are not conductive at all, you can hold it, you can shape it, and it stays hot for long enough for you to make a special shape. Okay? So here, for example, I can make a small spring. Yeah, in France, sometimes students have very strange idea about what to make with it. That's in the fun. Okay, so here I made 2 different springs, and you see that if you stretch the polymer, it will get to crystallize faster because you align the polymer chains and you help to make crystals. If not, you will have to wait to be below the melting temperature, that is 60, and maybe even below 40 Celsius degree for the polymer to start to crystallize. So if you have cold water or just running water, you can put a piece of the polymer in the running water to show that when you cool down the material, it will crystallize faster. So now I put my right finger in the cold water, and you can see that this is white and the other one stays transparent. Okay? And the whiteness of the polymer when it crystallizes is something very interesting to discuss with the student, to explain, because in their everyday life, they see objects that are white because of the same scattering of light phenomenon than in semi-crystalline polymer. This is a Millet scattering. So depending on the age of the young student, you can adapt your explanation. If the children are 5 years old, to explain Millet scattering can be a bit tricky, but you can explain that if you have two materials that are mixed together and that are a bit different, they interact with light differently. And due to this successive interaction with the two materials, it will scatter light everywhere. So this is an interesting point to discuss. The insulation property of polymer is another interesting point to discuss. The fact that some materials can be melted is another interesting point to discuss, because the polymers are not the only material to be able to melt. You can talk about metals and whatever you want, ice and water ice, I know. So this is an experiment that can last very long if you have people that can understand what you say about all the different aspects of this material. This material, as it is biocompatible and biodegradable, can be used to make orthesis, for example. So I assume that in Japan also nowadays orthesis like this one are made of plastic. So if you break your wrist, you need this kind of protection later. So this is PCL, exactly the same polymer. And when the guy who is in charge of making this needs to shape it on you, he puts this in hot water, it gets softer, and after that, he can do this easily. Okay, so this is an example. Of course, depending on your abilities, you might want to make a small art object with this polymer, or you want to repair things around you, or to make fast prototyping. 3D printing is very trendy and it's very useful, but fast prototyping with PCL is much faster, much cheaper. So this can be things to discuss. One thing that I bring with me when I go to explain Millet scattering is usually you can do it even with, for example, seed oil and water. This time it's toluene and water because that's the best working system. But of course, toluene is not so friendly. But here you see that I have two liquids that are fully transparent. And when I will shake it, I will have an emulsion of toluene inside of water, and it will turn white for a certain time. And when separation becomes large again, it will turn transparent on both sides. So this is a nice way to show directly why crystalline PCL is white, because of the presence of the crystalline phase, and why it is fully transparent when there is only one phase which is amorphous. So on this experiment, after this experiment, you can, I go fast on this, but you can speak to them about situations they meet in their everyday life. You can speak about the clouds, you can speak about the sea foam, you can speak about the snow, you can speak about all of the different foams made of liquid material, transparent material, air plus polystyrene, for example, that makes polystyrene foam to be white, air plus egg whites that make a white foam again, milk that every children has maybe seen, facial cream, mayonnaise. All of those systems are white due to Millet scattering. So depending on the age of the student, you can discuss with them about this scattering and which phase is present, if it's air, water, and so on and so on. Okay. Same for butter or for coconut fat. And same phenomenon to be possible to explain for egg white when it's heated and it turns white after heating. Of course, explanation associated with this whiteness of egg white and so on can be given only to children that are old enough to understand everything. So here now, when I talked to Nina about the fact that I wanted to do polymer in a school in Japan, she told me that maybe a good idea to interest young children would be to make food samples, because in Japan you are very famous for all the food samples that we can see in the restaurants. And at the beginning, I was not too sure what we could do, but as PCL, when it has the shape of a pellet, it looks like rice. I decided that maybe it would be possible to make onigiri. So what I did is I needed some PCL nori, which is not so usual. So what I did, I used my tools in the lab, and we have hot press 10 tons that can go up to 350. So I use this press to make I don't know what to say, to make caps of PCL, very flat layer of PCL. And of course, this flat layer of PCL was just transparent, like the PCL I gave to you. But on top of it, I mixed some carbon black and some green pigment I had. And after that, with this press, once it is melted and I have the pigment, I can roll it and try to mix by myself. And when it starts to crystallize, I put back to the press, and after 2 or 3 times, the pigments are well dispersed. But once it was finished, I had just a very flat layer of this color material, but I wanted it to look like nori. So I took this is polypropylene foam, and I don't know why, but it is nicely textured. And for me, I said, well, maybe it will help. So when the PCL is melted, I take two layers of this material, and I press in between, and it gives this texture that looks a bit like nori. So I can demonstrate enough, I hope, how to do this small nori. So of course, if you go to school and you start to do that, every children will want one, and every children will want to do one. So maybe it's complicated, but it depends. You can try. So to do it, I took the same material and I removed this part. So I can fill it with PCL drains. Okay. So once it is filled too much, I will pour some hot water on top of it. Okay. Maybe. Okay. So I pour hot water and it will keep its shape. I try not to burn myself. Okay. So just a bit and you see it becomes transparent. So after that, I need to put cold water to help it to crystallize. And water is not too cold. Okay. Once it will be crystallized, I can remove the square shape. I put a bit too much, so I can remove it from now. Okay. After that, I will need to soften the edges because it doesn't look like onigiri. It is too regular. So I put some hot water on top of it. First I put the hot water in here. I will dip just a little. I don't want it to melt totally. That way I can soften the edges. Okay. When the edges will be softened enough, I will need to put a bit of original PCL. Usually I will use the plate for that. And I want, because here when I soften the edges, we might not see that it's rice grains anymore, okay? So I want real rice grains, a real PCL rice grain at the outer surface. So I melt again a bit the outer surface and I press in contact with PCL grains and I press the one that wants to stick to my onigiri. And after that, to be sure that they stay stuck on the onigiri, I put back to hot water. And by doing so, I will make the outside of the grain and oops. And this time, I try not to hold it too firmly, not to turn the surface into something that is flat again, okay? I can put it a bit in cold water because now I want to add the nori leaf. And if I press against my onigiri that is very soft, I will break it down, okay? So I put it in cold water to make it hard enough, which is the case now. And here I did a bit of a mess, but it's okay. Now I will take a piece of onigiri, nori, a piece of nori, and on my PP layer, there is a special orientation that I want to keep, for example. So I put this piece of nori here, and what I will do is I will pour some hot water on my nori leaf and it will melt the leaf, and after that I will just press onigiri where it needs to be close. Yeah. Okay. I do again. Okay. So I put enough hot water to be sure to melt nori. And after that, what I have to do is just to press here, to turn and to press again, and not to touch it by hand, to avoid to put my fingerprints on the node. And now I have a new. After that, you let it cool normally, or you can put it cold water if you want to faster the process. So I say in few minutes, 3 or 4 minutes, it's possible to demonstrate this. And after, it depends if you have time to do it with children or not again, and so on and so on. So these are just pictures of what you saw, in case I couldn't make it live, but it was possible. So now we can speak about cross-linking. We have few experiments that deal about cross-linking of polymer. And one that is nice in France, when we go to very young children, they know this kind of diaper very well. And even for children that are a bit higher, they have little brothers or sisters who might use it again. So we can explain to them, sometimes my students, what they do is that they break this open, so we buy more, and they remove, inside of this, they remove white aggregates of polyacid acrylate, PAA, or polyacrylate acid. And this is the superabsorbent that is inside the cellulose of the diapers. So here, today, I will not break this diaper, but what I will do is I will put 3 grams of PAA inside this glass, and I will pour on it, I will top it with hot water. So that's hot water is not necessary. You could do it with cold water, but with hot water, the absorbing phenomenon of the polyacid polymer is much faster. So you can stir it, and soon enough, you will see that it will become more difficult to stir, and you can wait a bit, and you will see that my fork will stand up like this. So the polymer is a polyelectrolyte, and the water wants to get inside of it to equilibrate ionic concentration between outside and inside the polymer. So outside, I use plain water, so it contains ions, but much less than inside the polymer. So the polymer swells very fast. And here you see that if it was in a diaper, it would help to retain water. Of course, it has no mechanical properties because it is made of very small pieces of polymer that is a thermoset. It means that it cannot solubilize, but it's like if it was small pieces of glass that swollen. They can take 100 times their original weight in water, which is why they are used in diapers. So this experiment is very easy, very fast, quite cheap, and usually it impresses the young student quite well. After that, there is something that maybe has been popular in Japan too. It's this small bit that when they are in water, they turn much bigger, okay? And here I remove the water so that you can see the bead much better, okay? So this small bead becomes this big bead when they are swollen with water. So this experiment is something that my students do a lot because it's very easy, it's very visual, and once again, you can explain many, many different things depending on the level of the students. First thing, I asked my student to arrive with this bottle with inside water and beads that are swollen, and to have an empty bottle with them. I might use this one. Not sure it's possible. This empty bottle, I mean, not empty, but this bottle that contains only water. When they arrive, they could do this experiment. This could be the first experiment that you do in the class, which was not the case today, but it could be. And you show that we had little beads inside of this bottle, and the beads are small, they are easy to see, and they fall very fast. It would be better if I had, if it was full of water. Now we have water, but now there is air, and it disturbs a bit what I want to show. Okay. So when the bottle is full of water, better, it is easy to show that the bead falls very fast compared to these ones who fall much, much, much slower. So here, if your students are old enough, you can speak about density. The idea of Polymers in your school is not to speak about polymer only, to speak about science. So you can speak about density. When the small beads are dry, it's the density of the polymer, and it's higher than the density of water. But as soon as it gets full of water, the difference of density between the beads and the water decreases a lot. And the time it takes for the beads to go down decreases also a lot. Another point, but it might be more challenging depending on the age of the student, is optical information. As we have a difference of density between water and the polymer, we have a nice contrast due to light refraction when it enters the bead. So we can see very well the edges of the bead, okay? And even if the beads are transparent, we can see them. When the beads are swollen, if the beads are transparent, not colored, you don't see them at all. It would be better if I use only uncolored beads. That way you would see nothing. Okay. But this is something that you can show. And of course, showing the fact that when it is air and not water that is surrounding the beads, you see much, much better the beads because of light refraction also, because of the refractive index of air that is so different to the refractive index of the water beads. Depending on the age of the students that you visit, you can also speak about osmosis. This is how the beads grow when it's plain water, and this is the maximum growth when it's salted water. If you put a lot of salt in the water, you have ionic concentration that is high in the water, and the beads will will grow a bit, but not that much, and they will stop growing at this size. Once again, you can show the difference of, no, you don't show it. This one is packed, but you could be able to show the difference of density between water and the bead. Okay, I think I've done everything. So usually the children want to play with the bead, but the mechanical properties of the bead are very weak, and as soon as you press a bit too much, it explodes, okay? But in France, students, children already know the bead's properties and the bead, so they don't pass that much. It depends if they are used to play with it or not. Okay. Okay, so another experiment that can be fun in the classroom is this one. You need hot water, you need gummies. So gummies are quite popular in Japan. I think they are done with gelatin most of the time in Japan, in France too. It works better, what I'm not sure works better with gelatin. So These are French gummies, and when you look at the back of the bag, it says that it's about 6 grams of protein for 100 grams of gummies. And these gummies, they can dissolve in hot water. So what I will do very soon, as soon as the water is hot, I will put hot water on it, and you can arrive in the school with 3 boxes like this, 2 full of gummies, and 1 which is full of the gummies that has been dissolved in water, but that you put in the fridge the day before. So you have to prepare yourself. Here, I will put hot water on top of gummies, like this. And what you can do with the kids is to show that, avoid it on yourself. You can shake it and you can show to the kids that the gummies will disappear. Depending on the age, you can speak about a network of gelatin. If you want, you can speak about collagen that is present in the bodies of animals or human beings also, of course. So after, I would say, roughly 1 or 2 minutes, all the gummies will be dissolved in the water. It should go fast. If you let it stand, the issue is that after that, there is not water all around, and the dissolution might not be full. So that's why I keep checking this thing. I'm almost done. So once the gummies are dissolved in the water, the kids will never think this can be gelated again, because it looks so liquid to them. It looks like water. So they will never think it's possible to create a new network of gelatin inside of the liquid. However, if you prepare before going to make your presentation, if you prepare the day before exactly the same box like this, so now you see it's fully dispersed, fully solubilized. So if you prepare one at home and you put it on the fridge, you can show to the children that this is gelatinized again. And if you have a bit of hot water, it's quite easy to heat up the edges of the box. At the time you see some air to get infiltrated in between the box and the gel, which will happen soon. Yes, it is. And you can take this out easily and show that you've made a kind of jello quite easy. So you can show that you can treat it. Yes, yeah. Why not? This is jello. This is gummies plus water. Not bad.
Oh,
yes.
Question. Is this Teflon kind of box? Or?
No, it's polypropylene. That's the cheapest box I found. It's polypropylene. It's used for laboratory storage, I would say. And it's quite convenient. And once the gummies were 6 grams per 100 grams of gummies, 6 grams of protein, I tested that a gel with only 2 grams of protein can make something that looks like a gel. So as I put 3 gummies that was topping 25 grams, I see that when I go up there, it's 50 grams of water. So I have 1/3 of the original concentration of protein, and it works fine. Okay. So this is easy, and I think it speaks well to the children, because they eat gummies, they eat jello, because in Japan you have this kind of desserts quite often. So it's possible to use. After that, you can explain the network. Depending on the age, you can start speaking about hydrogen bonding if you want, and it depends how students are receptive or not. Okay. Another, and it might be almost the last experiment, This time, the idea is to produce gel with alginate, and in this box will be nice. So you know Kanten. In Japan, Kanten that we call agar, for example. It's coming from seaweed. Okay. In seaweed, you have gel that exists, and to produce Kanten or to produce alginate, what we do is we exchange the divalent or covalent ions that are inside the original gel by a monovalent ion, which is sodium. And we I made a sodium alginate solution. So sodium alginate is a powder, and I add this 5 grams of alginate for 1 liter of water. I add food coloring also to see better. And this is a solution of calcium chloride, CaCl2. So calcium has 2 charges, so that makes for him 2 arms to be able to cross-link, from a physical point of view, the alginates. So what I will do now, I will use syringe to drop sodium alginate solution in the calcium chloride. So I will drop slowly, small drops. I mean slowly, but it's not necessary to be that slow. And it will make small pearls of alginate. Because calcium will exchange with sodium, and it will make a gel, ionic gel. So if I push inside of the liquid, instead of making drops, I make spaghetti or ramen. So I can do, if you want it to be beautiful in front of children, you can use different colors. And the longest you will wait when you discuss with the children about the experiment, the longest it will give time to the calcium to replace the sodium, and the harder the gel will be. Same thing. Okay. So I'm not sure you can see, but for sure you see that it did not dissolve inside of the water. Otherwise, I would have a blue-red color of the water. So the food coloring dye cannot exit easily from this gel. And now, I think it's good enough. Mechanical properties are good enough. I will remove the water and put back gel inside of the box. And you can have a look. And usually the children will want to press it, to play with it. So in France and other countries, some in the food industry or in the nice restaurant, I would say, some people try to make caviar, fake caviar out of this. So the idea is to change the color, change the taste of it. So you can make a caviar or truffle or whatever you can imagine. And depending on the way you masterize the process, you will have something that is fully gelified or something that breaks and frees some liquid. So in Japan, we could make eggs of salmon, for example, with an orange color, and that would be appealing. There is no danger. The kids can eat it. I mean, the dye is not so good, but it's food coloring anyway. So they can find this kind of food coloring in the candies that they eat also. But here you go, and you see that the mechanical properties are not that bad. You start finally crossing inside of it. You can see some liquid that went out, but it's something that you can show the transition from a liquid to a gel very easily. Okay. So I think I'm almost finished. There is one last thing that I want to show that I didn't show during my lecture. Is something that is important, is also to speak to the young children about the fact that many polymers are coming from oil, and many objects that we know are in fact the same chemistry, alkane, but not the same chain length. So you can start with a gas that you use for cooking, propane or butane. These are alkane with 4 or 5 carbons. After that, you can increase the length and you have heptane, the liquid that you put in your car to gasoline. After that, you can increase the chain length up to, let's say, 40, 50, 100 carbons, and you will have an oil that is used to take care of your bicycle, for example, or engines, to avoid frictions. If you increase again, you will have wax. And if you increase again, you will have polyethylene. But all of those materials are alkane. They have the same chemistry. They don't have the same mechanical properties, of course. They don't have the same toxicity. It's possible to drink oil made to clean the car. It's not so good, but it's very dangerous to drink heptane. Okay. It's possible to chew wax. It's not so bad. Not so interesting either. So here I will light both materials. What? Easier to light a candle than to light polyethylene without burning yourself. Okay, the idea could be, without taking any risk, to show that the flame is about the same for wax and for polyethylene. Okay, and if I blow the flame, there will be fumes, and the fumes will have exactly the same odor. Okay.
I think this is a fire alarm.
Yeah. So
we want to send that.
Yeah. Sorry. Yeah. No problem.
Yeah.
Okay. So no smoke, no smell.
We can separate, so it's no problem. To come here.
Okay.
It's too close.
Okay, I understand. And there is water running down the just faithful. So this one is alarm and this one. Okay, so in between is possible.
Yeah.
Okay, so you see the color of the, and I put it in the water also. Maybe I should. Okay. So I was talking about the color of the flame. It's a yellow flame with a blue base in both cases. Okay, and of course you know the smell of candle when you blow it. Okay, and you maybe not know the smell of this when you blow it, but I will start with this to show that the smell is you're scared, but it's exactly the same smell. Did you get it? No. It's the same smell because it's the same chemistry. It's the same products. Well, this one you know.
Oh, yeah.
You get it?
Yeah, I understand.
So, yeah, of course. So this is a very easy experiment to open the mind of the young people, to tell them that the chemistry can be the same, but the physical properties are different, and toxicity is different, and so on and so on. So, for example, in France, if I would say to some friends, I will use a candle to light my barbecue, they would say, okay. And just after, if I say, I will use a plastic bag to light my barbecue, they will say, damn it, impossible, this is toxic. but it's the same material. Okay. Okay, I'm finished for this presentation.
If you have questions, you may continue.
In the class where you took the spoon,
Yeah.
so water is still inside or no?
Yes, the water. There is 1 gram of polymer and 3 grams of polymer and 300 grams of water, and the water is still in the polymer.
It's still inside.
Yeah.
Absorbed completely, it's interlinked or it's still there? It's interlinked.
It's absorbed in a way. How can I say that? It can be removed if you dry it. It's not connected in some way, but it just absorbed due to osmotic pressure. It wants to get inside.
Yeah.
Okay. So it is an interesting question. If we have the same problem as this one, if it's very salty, the water, it will not be absorbed. Okay.
This is also reversible. Like we can take out the spoon or not? No.
Yeah, we can take. There is no mechanical. The spoon was just here to show that it's a gel, but it's not crossing. It's small pieces of polymer that are swollen, but they are not connected to each other because they are cross-linked and they have their own life. But so it's like small pieces close to each other.
There's one more question.
Yeah.
Like in final, you just showed that polyethylene and wax has the same claim.
Yeah, same chemistry.
It's always say like the polyethylene always do more damage to the environment because gases are different. Like after burning.
I don't think gases are such different. The issue, I'm not sure I understand your question. When you say more damage, it's for health.
Yes, for the environment. Like it's always recommended not to burn the plastic.
Yeah, you're right. But in fact, I think it's bad to burn the candle also. No, I'm serious. We never think about it because we use it on birthday cake and so on. But if you have 80 candles and it means you are old, but if you blow them, you smell a lot of vaporized wax. And for sure, it's not good for health.
It's about the amount, like candle, the burning candle is not so big as compared to the polyethylene. The human beings use polyethylene used a lot.
Yeah, but I would say it's just it depends on the plastic you burn. If I burn this polyethylene bottle, I will not do it. If I burn the bottle, it will smell very bad.
Yes.
And this will light. It will make big flames and so on. This is very dangerous. Okay. But if I burn this plastic bag, which is made of polyethylene, it's not more dangerous than burning a candle because the fumes are anyway small molecules. Otherwise, they cannot be fumes. Okay. So they are small molecules in both cases. That's why it smells the same, and it's not more dangerous. But the issue is that you cannot say to people, no problem to burn plastic bags made of polyethylene and problems to burn, I would say, plates made of polystyrene. Of course, polystyrene will be very bad for your health, but polyethylene is not. But you have to have just one message to the population, is don't burn plastic, please, which is what we call. Any more questions?
Do you think you can replace this wax to the biodegradable material like the sugar and?
I don't know. I use the wax to show the similarities with polyethylene, but maybe we could use other products than wax made of oil, made of petrol. I know that some wax can come from maybe rice. I think that there is rice, yes, and or soybean wax also. But I'm not so sure it will be better for health or not to release the fumes of this other type of wax. Because maybe the chemistry is not so much different. I'm not sure. They're two different. Yeah, but you can have, maybe as you have, in France, most of the wax that we use are from oil. But if in Japan you have waxes that come from soybean or others, it would be interesting to check on the chemistry.
Yes. And also, in terms to interact more young students to like science, I think this like only creation, maybe the workshop which you can use your creativity will be the best, and because it's really powerful. For sure. To do something you were told is super boring, so that's why they want to make their own like stuff.
For sure, we have a very nice example here. Yeah, I can show your output. So here I show how to make a spring around my fingers, but she did this really nice output, and I think if you are, it's another way to do this popularization of polymers in your school. You could, for example, decide that you only bring PCl, hot water, and at the beginning you melt it and you give, like I did, pieces of PCl to every student. You ask them to do their best, and you can show this very fine output as examples. And after that, they do whatever they want. And you show them that it's possible to recycle polymers because you boil more water, and you ask them if they are pleased with what they did, they keep. If not, they put back in hot water, you mix, you give back, and they do again. So to show recyclability of polymers, it's very nice way to do. As I said, today I presented 11 experiments. But you can choose just one and to expand what you explain with it, depending on the age of the student. Everything is possible.
I see. Thank you.
Thank you.
Another question. So, ECL.
Yes.
So this crystallized, so that's why you see a lot of scattering.
Yeah.
But is there any polymer that can be like you can use it for handcraft, but it will be transparent, which is crystallized. Then you can combine those two, and because if you want to make some objects, sometimes the things are transparent or semi-transparent.
You're right. I've seen some. I have to admit that I didn't check what was the chemistry, and I assume it was more going over the TG of the material than going over the melting temperature. I think that the polymers that are transparent and that could be used to make this kind of artwork are not semi-crystalline. They are amorphous ones. Usually the issue, it depends on the molecular weight and so on to decide about the viscosity when you go above TG or above melting temperature. But I know that some polymer like this exist that can be reused and that can turn soft when heated. So the issue is I don't know what interaction there will be with PCl. If it is a polyester, also it will stick to PCl. If it's something that has no carbonyl function, maybe it will not stick, so maybe it will be difficult to use them together. This has to be checked.
So you have not thought of any other combining, let's say, some basic of optics source with these experiments?
I'm not in the optic field that much, so maybe that's why. In Polytech Grenoble, during some of my lecture, I show that we can control the whiteness of the PCl by controlling the shape of the crystals. So I could, for example, melt half of this in hot water, this is also a good way to show that the heat conductivity is very bad, because you pour this in hot water just like this melts and this stays crystalline. And if you put back in liquid nitrogen, for example, you have a much lower crystallization temperature. You cannot keep it amorphous, it's impossible because it crystallizes very fast, but you will have a lower crystallization temperature and you will have much more nucleation. And if you have much more nucleation, you will have so many nucleus everywhere inside of the material that they cannot grow like spherulites, they cannot grow like lamella. They stay very, very small, numerous and small, and the materials stay transparent. And it's final, it will stay transparent. But it's not easy to use this as a way to get transparent part, because you need liquid nitrogen, and it's not so simple. But I use it to teach optical properties of material depending on the size of the crystal. But what you had in mind was certainly something else. And
but you had already referring quite a few optics.
Yeah, refractive index and so on. I think depending on your background, using this experiment, you can talk about many other physical aspects of science. So some of you are interested, I'm speaking to the students, of course, interested in trying to do science popularization in junior high school and high school.
I'm all for it.
You're on for it. That's good. She has no choice. You're on for it too. So,
I'm not staying so long, so I don't know if I'll be here or like able to do. But
okay, when you're here, you can maybe try. She was one of my students.
I did it in France.
Yes, you did escape game.
Escape game, yeah.
But it was a bit more complicated, but
Not to the kids, to the high school.
So the escape game is quite popular in Japan.
oh yeah.
Yes.
No.
Maybe.
So you have to develop the Japanese version of the French escape game.
Okay.
That's big work.
So what is that game? Any idea? I mean,
Yeah.
escape game? Any?
Nina can explain a bit if she wants. No. Okay. So the idea is with also the experiment, you imagine something tricky, so that the students need to think about a way to understand a bit polymer to find to escape a room. So, for example, one experiment is using this super absorbent. We tell them that there is a box and it's full of very dangerous liquid, and in the box there is a key, and they need to remove the key from the bottle without touching the liquid. And they have this kind of magic polymer that is available. So what they need to do, if they understand well, is to pour a bit of the super absorbent polymer in the water, shake it, turn upside down so that the key gets fully down, wait for everything to turn into a gel, turn, open, and the key is here on top. So they don't need to touch the liquid. So this is one experiment. This is one part of the game. And I think there is 7 or 8 steps with experiments.
Yeah, 6 was the
6 or 7. So one is with a PCF. You have like a candy made of PCL, and you have different colors. And another part of the game lets you know what color of candy you should melt and open to have a number that is written inside. There is one with the TG. We have different. This when I show you it was flat, and after that I twist. But this is the other way around. They have samples like this that are already twisted of different material, and some of them are made of PET, and they will untwist. And on them are letters that are written, and the one that untwist has the letters that you need for the future game. And other samples are made of polystyrene and PMMA, and they will not twist because their TG is higher. So these are the kind of small games. But what is tricky with the escape game, the Polymers in your school, is that you need to make the full story around it and to take care of the players, to know when to help them or not. So that's another, but it's good because it's a game, and games are popular indeed. Okay, so we have two. We need more.
The spawns is available in France, not in Japan.
When I checked Amazon,
They have.
not that yes and no, because we have exactly the same one in Amazon,
Yeah.
but I couldn't find any other thing. It's not very common or popular.
Okay, but you can buy it on Amazon
Yes,
in Japan.
yes, but 5 pieces costs like 6,000-7,000 euros. It's
That's a bit expensive. In France, I don't know this one, but I try to buy it when it's for sale, but because I buy 10 of them each time. It's something like 500 yen per small. So this is okay. You can buy 10 for 5,000. Okay.
maybe when I come out from
Yeah,
France.
this is nice. You can bring back buy it. Okay. So maybe some of you are too shy to say how much they want to participate. It's possible. So no problem. You will tell Kushida Sensei later. Okay.
And also maybe tomorrow there will be San Sakura in JST and in Telephone Center. No, not JST Center. So Odaiba in Tokyo. That is the biggest outreach in science event in Japan. So maybe we aim to try participate next year just to show those kind of things and it combined with story like escape game or if it's possible. I don't know, space is limited.
Yeah.
Of course, to attract it's always better to combine. Not only you don't want to do take class, but
Yeah.
game.
Make it like a game. Yes. So that's a good source of motivation to participate in this event.
Yes.
And maybe, I don't know, Kuroda Sensei, maybe it could be possible to imagine some credits for this activity or some certification. Is possible? Good. So maybe that will attract more students if they know that they...
No, such kind of left the curriculum, but it's
Okay, that's good. So,
Another question.
yeah,
You said this you have been doing since last 10 years or something?
yeah, 11 years, yeah.
So is there a feedback from any students who have undergone this demonstrations?
My feedbacks are usually very good from the students. You mean the ones that are in Polytech Grenoble as a teacher, or the younger one?
Yeah, the ones who saw that demonstration and now they are, let's say, at higher studies or something.
Well, unfortunately, I have not followed them because it's about 1,000 a year, and I have not yet met somebody who tell me I came to your engineering school because of this activity, or I want to be a polymer scientist. But 11 years. If we say that the average age of the students is around 12 or 13, so it means that it should happen one day. I hope so. But I have met during my personal life several teachers in high school, junior high school, that talk to me when I say I'm a polymer guy. They talk to me about the project, and I say, it's my students. But that's nice. That happens. This happens every year because I meet collaborators at different levels, with different opportunities.
Do you have a name of the project or a logo of the project?
Oh, in France, yes, we have. This is here is the logo. I don't know if you see it. It's a P, like the P of Polytech, but made of something like this. In fact, but it's twisted. Made of made of this, but it's twisted to make a P. Okay, and so in French it's called des polymères dans ton école, which means polymers in your school. That's the name. Of course, in Japan, you will have to find your own name and own logo and so on. But
Can we access this video on?
yes, yeah. All of these videos are on YouTube. And if you type des polymères dans ton école, so if you type polymère école, school is école in French. And if you type polymère école, I assume you will find there is something like 8 videos. And this was during COVID time. During COVID time, we couldn't go to the schools, so we made a video and we sent package of small PCL and so on to the teacher, and they look at the video and they could do in their school. So it was a lot of work to make a video that first shows the experiment, then show what you need to do the experiment, then give the scientific explanation. Unfortunately, this is in French, but it is very visual, so I'm sure you can understand, and I've shown to you. And maybe with artificial intelligence nowadays, you can translate everything very fast. Okay, thank you. If no more questions, thank you very much.
The lab goes in development Professor
Okay. Yeah, first, thank you very much, Dr. Vincent, for having 3 lectures in this week. One is for undergraduate students, and one is for graduate students, and that's why it's today for researchers and graduate students. And yeah, it's very important. I think, especially for undergraduate students and the second year students in the class, they directly see what happened in polymers or materials. So it is very good experience, not just reading the textbook or make a test, but can directly have an experience that materials are behave like that. So this is very important experience. And also even us researchers are also people all have some experience that doing experiments they associate or is impressed by some phenomena. So this is a very important point for research for the persons. So yeah, in that meaning, this kind of lecture is also very important. And also in Japan, we want to do similar kind of classes. Yeah. Anyway, thank you very much. This is thank you.
Thank you for giving me this opportunity, because I have to admit that this lecture I did here, I never did it anywhere else. It was prepared just for Japan, because in France I have my lecture, traditional and so on. I tend to do experiments in my rheology lecture, for example. I tend to do experiments when I'm teaching practical work with my students. But I never gathered all the experiments to make a class based only on experimental presentation. So thank you for giving me the opportunity to work on that, and it was very nice for me too.